QZ3 next week. This will include some stuff on electrochemistry, depending upon how far we get with that topic. Today, Friday, Monday, lecture class. Also, the due date for Special Quiz 2, as stated on Special Quiz 2, it's Tuesday. You want more time?
Yes, please.
All right. I didn't get this developed quite as soon as I had hoped to. So you can add a week.
The date is April 1st.
Oh, pardon me. See, we won't make it due on April Fool's Day. Now, even though I've added a week for Special Quiz 2, and a lot of what you will do on Special Quiz 2 will get you prepared for exam number 3, which is next week. Don't let study for exam 3 and your doing of Special Quiz 2 interfere with each other. Let's be diligent about this stuff. I know daggone good and well some people deal with these special quizzes the day before they're due. That's not the way to operate. Now then, back to thermodynamic analysis based on thermodynamic property information. The NO2, N2O4 equilibrium system, which we've examined previously, have recognized from our G-state graph for this system that if this system is studied at 25 degrees centigrade, total pressure 1 atmosphere, about 20% of N2O4 would dissociate if we were able to develop this system by starting with pure N2O4 on getting us to equilibrium. Let's see if we can do a calculation to verify that. Now, question 39, as it's stated in the notes, I believe, is for this very same system, of course, but with the reaction equation written in the opposite direction. That doesn't matter. With the reaction equation written in this direction, this is the equilibrium constant expression for which the units will be atmospheres to the minus 1. The value is 6.69. Where does value come from? Came from this. Delta G 0 comes from delta H 0 and delta S 0. The temperature is 298 K. R is a constant. Put in the numbers, do the arithmetic. Do it. You need to practice. Now then, to pursue this analysis, we need to pay attention to Boyle's law. Pardon me. Dalton's law. Dalton's law of partial pressure. Dalton's law of partial pressures, which has two perspectives. Do you remember the two perspectives? Perspective number 1, the total pressure for a gas system is equal to the sum of the individual component gases. The sum of the partial pressures for the individual component gases. Well, this is a two-component system, simplest possible mixture. Total pressure is 1.0 atmospheres. So this, the total pressure, must be equal to the sum of the partial pressures for N2O4 gas and NO2 gas at equilibrium, because they're the only two-component gases of this system. So we can write that the partial pressure of one of the components is equal to 1.00 atmospheres of total pressure less the partial pressure of the other component. So I did that for partial pressure of N2O4 gas. So we'll go back to our equilibrium constant expression. With this substitution, convert the equilibrium constant expression to one unknown and solve it. In this case, to get the partial pressure of NO2 gas, from which immediately the partial pressure of N2O4 gas follows. These are the values. And of course, the sum of these have got to be 1.00 atmospheres, as is the case. Now then, Dalton. What's the second aspect, perspective of your law, which we have to pay attention to carry on with this analysis, because we've got the equilibrium partial pressures, but we want equilibrium composition, which means for what we want for this system is moles. Now, based on the experiment we did, we considered in one cylinder, piston cylinder, to start with 2 moles of NO2. And the other, we started with 1 mole of N2O4. Wouldn't make any difference. We get the same result. So in this case, we're imagining to start with the 2 moles of NO2. Again, as this problem is stated in the notes, you would imagine starting with 1 mole of N2O4. And the value for the equilibrium constant would be the inverse of this, and the inverse of this. Nothing fancy about this. Could we get at determination of system composition with PV equals nRT? Yes or no? We want to calculate system composition. We want moles. So after we start with 2 moles of NO2, and initially no moles of N2O4, we already realized that what will happen is a good number of the NO2 molecules will get together, react with each other, dimerize, and become N2O4 molecules. So, when equilibrium is established, how many moles of NO2 molecules will remain, and how many moles of N2O4 molecules will it form? Can we get at this with PV equals nRT? No. The answer is, I heard no. No. Is it correct that it is not possible to calculate the system composition with PV equals nRT? Or instead, do some of you think we can succeed with applying PV equals nRT? I'm asking you. Remember, your success as a student depends upon your ability to answer my questions, not my ability to answer your questions. I'm the one being enriched here. You're the teachers. I'm the student. I ask all the questions, and you better answer every damn one of them correctly. Otherwise, I'm going to get mad. I'm going to go on strike. I'm going to be an angry student. And what am I going to write on my placard as I'm on strike? Students unfair. What's wrong with PV equals nRT? N is the part we don't know. We've calculated P. We know the temperature, that's 298 K. What about V? Will we know V? Hell no. If you don't know how many moles you got, how can you know what the volume is? So with PV equals nRT, you're stuck. You got two unknowns. So back to the second aspect of Dalton's law, which is what? On what does the partial pressure of a component gas of a gas phase system depend? Tell me, Dalton.
Mole fraction.
Mole fraction, you betcha. What's mole fraction? Moles of a component divided by total moles. All right? Well, this is a simple system, again, with which to deal because it's only got two components. So we can write P component equals, remember this? You saw this in 2045, I think. This is capital Greek letter chi. What's it mean? Mole fraction. That's it. This is the second aspect of Dalton's law. Partial pressure of a component gas in a gas system is equal to its mole fraction times the total pressure. All right? Well, we got partial pressures, don't we? Let's see, which way did I do this? Partial pressure of N2O4, partial pressure of NO2. I did partial pressure of N2O4. Get this out of the way. Okay? So I'll go back to our favorite unknown representative in algebra class, x. X marks the unknown. And say that X is equilibrium mole quantity of N2O4. Based on this, at EQ, moles of NO2 gas is equal to how much? How many moles of NO2 gas did we begin with? 2.0 moles, right? And to establish equilibrium, how many moles of NO2 disappeared? How many moles of NO2 gas disappeared? You see that reaction equation? Doesn't that reaction equation tell you that by this transformation, if you wish to make a mole of N2O4, how many moles of NO2 you got to use? 2. So if we decided we're going to consider making X moles of N2O4, how many moles of NO2 we got to use up? 2X. So how many unknowns are we now going to wrestle with? Because here's my relationship. Up here I got X. Down here I got X plus 2.0 minus 2X. What unknown? We can solve this. So we get let's see. I wrote it here someplace. There it is. Minus twice 0.81. Now bear in mind, we said, had we pursued this investigation by instead starting with 1.0 moles of N2O4 and 0 moles of NO2, that's the way we described the experiment that we were going to do for this system with the piston cylinder gadgets, we get the same results. So had we started with 1.0 moles of N2O4, we still would wind up with 0.81 moles of N2O4 at equilibrium. So percentage-wise, how much of the N2O4 disappeared? Well, 19% really. But isn't that pretty close to 20%? Didn't our G-state graph show that for the experiment that we conducted, imaginary experiment, we conducted with the two piston cylinder apparatus, one starting with 2 moles of NO2, the other starting with 1 mole of N2O4, each at total pressure 1 atmosphere, and temperature 298 K. G-state graph showed about 20% of the N2O4 dissociating to get us to equilibrium. Now, how did I really find out when I made that G-state graph that about 20% of the N2O4 dissociated to get us to equilibrium? I had already done this arithmetic, because that's where the percent dissociation comes from. Tell me. Let's talk about other experiments we could do to get at this. Remember what we did here? We imagined starting with 2 moles of NO2 and nothing else. Or we imagined starting with 1 mole of N2O4 and nothing else. Well, I can talk about starting with any mixture of these two system components. A mole of N2O4 and 2 moles of NO2. That keeps with the coefficients on the equation for the reaction. What would happen in this system? Is this system at equilibrium? Do you believe that equilibrium reaction tells you that if you make a mix of 2 moles of NO2 and 1 mole of N2O4, the system is at equilibrium? Yes or no?
Yes.
Really? Didn't we just find out that we're going to get this system to be at equilibrium when we've got more than twice as many moles of N2O4 as we have NO2? Can we find that out? 0.81 moles of N2O4 and 0.38 moles of NO2. Right? We just did the arithmetic. Let it talk to you. So we'll write. Thus, EQ mole ratio at P total equals 1.0 atmospheres and T equals 298K is this, isn't it? Or EQ P ratio. That's the equilibrium partial pressure of N2O4. This is the equilibrium partial pressure of NO2. This mix correspond to this? Hell no! This tells us, gee whiz, for this system to be at equilibrium at 298K, the ratio of moles of N2O4 to NO2 must be on the order of 2 to 1. It's a little bit bigger than 2 to 1, isn't it? 0.81 divided by 0.38 gives us a number that's a little bit bigger than 2 to 1. So what's going to happen if I start with that system? I start with 1 mole of N2O4 and 2 moles of NO2. What will happen in this system? Is that system at equilibrium? No. So something's going to happen to get us to equilibrium. Because equilibrium is the most stable thermodynamic state in which a system can exist. So what's going to happen? Reaction is going to happen. What reaction?
Dimerization.
Dimerization will happen. NO2 molecules will react with each other to become N2O4 molecules until I get this mole ratio. All right? Let's start with this system. What's going to happen here? Anything? This at equilibrium? Will I get as much reaction in this mix as I did in the previous mix? No. But here I will still get reaction, won't I? Because we found out the equilibrium mole ratio is a little bit bigger than 2 to 1. So there I'm going to get some conversion of NO2 to N2O4. But if I start with this mix, something going to happen? What's going to happen? N2O4 molecules are going to fall apart. That's it. Hey, we're just letting this talk to us. No more, no less. Okay, enough on that. Now then, based on the information I got from the discussion class instructors for yesterday, everybody at least got the problem 21-1, and some got through it. Now what immediately preceded problem 21-1? Yesterday it was demonstrated for you that another thing we can achieve with this thermodynamic property information, I told you there's more chemistry stored in the thermodynamic property data table than in any other single data compilation. And I'm sure that statement is correct. Back in chapter 18, the only K values we discussed were K values for hydronium ion and acids weaker than hydronium ion. And we said at that stage of the game, whatever the K values are for nitric acid, hydrochloric acid, sulfuric acid, and perchloric acid. Those were the four acids. Those are the four acids listed in our acid-base table in the acid column that are stronger acids than hydronium ion. I could build a more comprehensive table, but that's not necessary. All we said was the K values for those acids are damn big numbers, which is why, practically speaking, even at initially high molarities, they will ionize by reaction with water to extents which are 100%, practically speaking. If you go to 2 sig figs, it is 100%. So with that, the first thing you looked at yesterday regarding this consideration is Ka for nitric acid. Got a big number, didn't you? It was on the order of 10 to the 5th. It was something times 10 to the 4th. I think 8 times 10 to the 4th, something like that. 8.3. And we said, well, what if you took the thermodynamic property information and calculated Ka for sulfuric acid? If our acid-base table lists these acids in correct order of increasing strength, then we got to get a bigger Ka value for sulfuric acid, bigger than that for nitric, because sulfuric acid is positioned above nitric. I don't know if the discussion instructors gave you that. You can get at this from the information in the thermodynamic properties data table. And if my memory is right, you'll get 3.6 times 10 to the 11th. Whoop-de-doo. You better believe sulfuric acid in water solution. As long as you got enough water molecules in there to do the job, that stuff's going to ionize. And the other acid, with which some of you had time to wrestle yesterday, was Ka for HCl. Again, if the acid-base table has got a correct strength order listing for the acids with which we are presently concerned, then Ka for HCl will be bigger than that for nitric and smaller than that for sulfuric. You get something on the order of 10 to the 6th. I think it's 2.1 times 10 to the 6th. 2.0 times 10 to the 6th. Close. Now, I've seen a number of acid-base tables in textbooks that state that HCl is a stronger acid than water than sulfuric acid. I have no idea where the hell they get this. Because the thermodynamic properties data table says baloney to that. I mean, HCl is clearly a very strong acid with a Ka on the order of 10 to the 6th. But 10 to the 11th for sulfuric is a heck of a lot bigger than 10 to the 6th for hydrochloric. I mean, it's one of the things you run into if you do science. You get data from all kinds of different sources. And the bottom line, as I have warned you, is if you wish to be successful as a student of science, you must perpetually be a skeptic. Carefully criticize everything. Take nobody's word as correct. Because Mother Nature couldn't care less what we say, what we think, what we believe, and what we write on paper, or what we calculate. Mother Nature does not give a damn and never will. Molecules behave as they behave, and it's our obligations as true scientists to find out how they behave. And we have to make measurements to answer these questions, and measurements can oftentimes be difficult to make accurately and reliably. So, you got to be critical all the time. All the time. Now, what do I know? Maybe there's some I know there's missed data in the thermodynamic properties data table. Is some of this missed data associated with these acids? Possibly. I have not the time nor wherewithal to go back and do all these experiments myself to make myself, put myself in position to be more happy with the data. You just don't have time to do all that stuff in science. That's one of the reasons why you find out these days that with chemistry having exploded into the huge, huge field that it is, same for physics, research always, I mean not always, but often develops a very narrow focus. Because there's so much to do. You know, so graduate students, I think, sometimes are shortchanged because they focus on a particular problem, and in so doing they forget all this other stuff that's out there to think about. Is it right, wrong, or indifferent? Well, I think it could be better. It should be better. But what the heck? No matter what we do, it can always be improved. Me, if I get the time, and I intend somehow to make the time, intend to do a lot of fundamental investigations into activities, because I like water solution chemistry. To me, that's the most important stuff, the most fun stuff. So, given the opportunities to pursue such, that's what I'm going to do. And activities is a big damn can of worms, I tell you what. Because in sum, what you're trying to do is to see how the behavior of one particle in liquid solution affects the behavior of all the other particles in the solution. And by damn, that's tough. It's a lot easier for gases. Chemists and physicists have developed very good equations for describing the behavior of particles in the gas phase, because among and between particles in the gas phase, there's a lot of space. So you have the advantage of being able to focus on how the behavior, on describing the behavior of a single particle. Because in a very dilute solution of gases, each gas is behaving independent of each other. That's called ideal. When you get into solutions, now you've got a real problem, because that's a condensed phase. If you take a giant swimming pool and somebody does a belly flop in that end of the swimming pool, and the swimming pool is 100 yards long. Woo, that's a football field-sized swimming pool. Sooner or later, that belly flop, the result of the belly flop is going to translate to every other particle in that water solution system. Now you're dealing with activities, and that ain't easy. I don't care. That's what I'm curious about. So that's what I'm going to fool around with. I've already done some fooling around with some of the gadgetry we've got around here, and the results which I have obtained are worthless. That's not going to stop me. I'll keep going at it. And as I said, one of the beautiful aspects of science is it'll never bore you. It might bore a hole through you. It's so damn difficult, exasperating. It can frustrate the hell out of you. Oh, I did this experiment. I didn't get it. I had an organic chemistry professor at the University of Toledo who at that time was chair of the department. He was also the oldest guy in the department. I heard a very interesting story about that fellow when he had been, I believe, a postdoc. He was intending to make an organic compound by a well-known preparatory route, a well-known synthetic method. But he was using compounds in this synthetic method which had not been investigated before by this synthetic method. He knew what he was trying to make. So he ran the reaction. It was a nice clean reaction. Got one product, but it wasn't the product which he wanted. Now what should he have done? He should have said, He should have scratched his head and said, man, this is neat. What's really going on here? He didn't do that. He got frustrated. He let the frustration cloud his thinking because he wanted to make this product. He didn't get this product, he got a different product. So he ran a reaction again. And according to what I heard, in his frustration, he ran it more sloppily. And he got some gooey junk. And he says, well, maybe the gooey junk is better. How could a gooey junk be better than the nice, pure, nice stuff, okay? And he did it again and again. And wound up never succeeding in being able to make the stuff which he wanted to make by this process. Well, for those of you who go on and study organic chemistry, you will certainly talk about the Diels-Alder condensation reaction. Because a few years after he walked away in frustration from this, a couple of guys, two guys, Diels and Alder, worked this up and won the Nobel Prize for it. How about that? A very important reaction, the Diels-Alder condensation. You'll study about this in organic. He had it first. What did he do? He let stupidity overtake his noggin. You do that in science, you lose big time. There's an example of losing really big time. And after we were told that story by another faculty person, he said, don't ever mention this. Don't do it. Because he was still mad about it. He should have been mad, damn mad at himself. But had he thought, all this madness wouldn't have happened. Once you shut the mind off in science, boop, down the drain you go. In any case, this analysis I'm going to post to Sakai. So for those of you who didn't see it, you can look at it in detail. And again, it's a case where the calculation is neat, interesting, because in the HCl case, the problem you run into is HCl is a gas. And what you wind up wanting to know is how much HCl is remaining for the HCl solution. Well, then you got to do some conversions here from phase, gas phase to liquid phase. And that's part of this calculation. But because of the complexity of the calculation, I wouldn't ask you anything about the calculations on a quiz or exam. It takes too much time. All right? So, again, if you didn't see this, take a look. I'll post it up this afternoon on Sakai. Special or challenge problem 21-2. Again, a few of you got to talk about this yesterday, but I don't know how many did. The true nature of the hydrated proton. This isn't right because of the positive charge density of H+. And I have said, well, then we got to use at least this, because this shows a water molecule, at least one water molecule, gluing to H+. A lot of rather fanciful studies in chemistry done in recent years have suggested this is the true nature of the hydrated proton, or even this, or even this. Some people have argued vehemently that this is it. I don't buy this. I don't buy this, I don't buy this, I buy this. Why do I buy this? What do we talk about at the end of chapter 19? Lewis acid-base chemistry, which is really an introduction to coordination chemistry, because it involves the formation of coordinate covalent bonds. Remember that? Well, here's H+. How many coordinate covalent bonds can this thing make? How many empty valence orbitals does it have? One. So, one water molecule. And my attitude is, to hell with these. I don't care what you do with your fancy calculations, I'm not believing it. Now, I understand that the hydrated H+ might in fact travel around like this, because there's still a hell of a lot of positive charge density associated with this, and the other water molecules might accumulate around hydronium ion and give this. But to me, the formal hydrated H+ has got to be hydronium ion. It can't be any of these other things. And until these people take the fundamentals of Lewis acid-base chemistry and tear it all apart and reinvent it, I'm not taking these. I'm taking that. Enough said. Back to this. Challenge problem 21.3. K for this reaction is partial pressure of CO2. And we found out what the K value is at 298 K, where we started with the temperature being known. And then with delta H 0 being set equal to T delta S 0, we found out what T is for this reaction if it's at equilibrium under standard state conditions. Because under standard state conditions, K is 1.00 atmospheres. What if I wanted to get the temperature for this system with K being this number? What would I do? Can I use this straight away? Remember, this depends on T, doesn't it? So if I don't know T, straight away I can't know this. And this is what I'm trying to calculate. Problem, isn't it? How do I get past this problem? Can I write this in its other form? I know this, don't I? I'm taking that as an isothermal property of the system. And I know this part, don't I? Because we're also taking that as an isothermal property of the system. How many unknowns have I got now? How about that? And the log of K for this equilibrium constant, what's the log of K?
3.
What is it?
The pressure of the...
What is the log of K? I want the number. -3. Now you can do it. That's all there is to that. I was only wanting folks to keep in mind, doggone it, that delta G0 is fundamentally this. That's all. Enough said. Chapter 21. Redox reactions. What's a redox reaction? Reaction in which ONs change. What are ONs? Oxidation numbers. Ox numbers. So knowing ox numbers, being able to determine ox numbers is often important in studying redox chemistry. Damned important, this echem stuff, because redox reactions constitute the largest category of chemical reactions. And most reactions which we use to give us energy are redox. Even though acid-base reactions are daggone important, and we've discussed those in detail, you don't get much energy out of acid-base reaction compared to redox reactions. When we eat food, and food reacts with oxygen in our system, this is redox. All right? So the question is, what is the best way to get oxidation numbers? And the answer is, memorize a bunch of rules, the likes of which you learned in Chemistry 2045. Where do those rules come from? They come from electronegativity. We know about electronegativities now, don't we? But the best way to get oxidation numbers is not by memorizing all those damn rules. It comes from Lewis structures. Right? How about that? Nitrate ion. Lewis structure. Those are formal charges. They're not oxidation numbers. And since they're not oxidation numbers, after I put them in, I'm going to take them away. And we'll do this. Just to remind you that the charge on the entire nitrate ion species is -1. Comes from the sum of the formal charges. You know this. So here's our Lewis picture. What do we do to get the oxidation numbers for the component atoms? You go to each bond site. of which there are 3. 1, 2, 3. And at each bond site you parcel electrons. You parcel electrons so as to give the electrons entirely to the atom of greater electronegativity. How does the electronegativity of oxygen compare to nitrogen? Oxygen is more electronegative, isn't it? Zip, zip, zip. That's it. And now we can get the oxidation numbers. Oxygen. Oxidation number for the oxygen atom. You go to the Lewis structure after you've parceled the electrons. Okay? You look at the periodic table. And you start by writing down the number of valence electrons which the atom has as an isolated atom. How many valence electrons for an oxygen atom? 6. And then you go to your Lewis structure after having parceled the electrons, and you subtract the number of valence electrons which the atom in question has after you played this parceling game. Each oxygen now has how many electrons? And then keep the sign straight. There it is. -2. That leaves nitrogen. 5 for the isolated atom, and after parceling, it ain't got any. Done, +5. Okay? So, to follow up with this, in preparation for our next chat, I want you to determine the oxidation numbers for acetic acid, for which this is not the correct formula. For every component atom of acetic acid, in particular the carbon atoms. And then, after you do this, I want you to go to question 22.2. And do it. Start of next class.